Hello everyone, welcome to my YouTube channel, Black Box Engineering. So this will be the kickoff to the electronics design that I was going to show you. I'm going to describe some of the basic concepts first to get into the more in-depth details. I just think it's important to cover basic terminology before I get into the um, specifics, I guess. So I wrote a forum post back here on digikey.com about radio frequency terminology, so I'm going to be talking about that first. So the first thing I want to tell you is what decibel means. Decibel is a unit of measurement to express a ratio of one value to another in a logarithmic scale. So other than a linear scale, which is like 1, 2, 3, 4, 5, logarithmic typically talks about like scales of like to the 10th power, like 10, 100,000, and so on. It just allows for a wider range of measurements, but without having to actually list every single measurement between those. It's just a compressed way of talking about signal strength because numbers get very large when it comes to that. Um, so, but the thing is, decibel is more of a generic, like description. There's actually a lot of different forms, such as decibel amps, dBA, decibel volts, but usually decibel is unitless. There's a lot of different suffixes that are added when we were talking about different things. So dBm or dB are when we're describing power or watts in an RF application. The M usually calls out the prefix milli. RF power measurements don't measure very high, but it does depend on the application. But dBm tends to be more common. dBi, so this is the content. I wrote this kind of out of order, but I I remember this now. So dBi is to describe how much gain a directional antenna has. It can either be a positive number or a negative number. I believe a negative number means it has very high directionality, meaning an antenna is shaped a very specific way to work in like it's like if it were pointing at another tower or just a general broadband like widely spread signal. Antenna shape is very important when you get into RF design. I don't remember the specifics, but anyway, so frequency range is the effective frequency where an antenna operates. There's a minimum frequency and a maximum frequency for antennas. An antenna will give you a range of frequencies, and it will be most efficient on center frequencies. It'll typically give you either just one value, like 10 megahertz or 20 megahertz or whatever value. Those are the center frequencies that they're the most like effective at. It doesn't mean that it won't work at different frequencies, but rather that it'll try to maximize the center frequency. Center frequency though, it's just the largest signal strength possible, the most amount of gain an antenna has. Um, some antennas are actually capable of having multiple center frequencies. They may be capable of doing broadband communication. You do not need to match center frequencies when you develop an application. It isn't quite feasible always to get the exact frequency, but it is best to get closest to that center frequency as much as possible. Otherwise, it will not pick up the signal as well. Um, bandwidth. Bandwidth a is how we describe a range of frequencies that an antenna or system can operate at. Um, You can calculate bandwidth by taking the maximum frequency, subtract it from the minimum, and that is equal to its own bandwidth. For example, if an antenna has a minimum frequency of 1 megahertz and a maximum of 50, the total bandwidth would be 49 megahertz. The one thing about bandwidth is you cannot guess at a frequency range if you're only given bandwidth. You have to have the minimum or the maximum to derive the other if you also have bandwidth. Another concept is something called band pass and band reject. I'm going to pull up my computer screen to show this because it's a little bit harder to describe in words. So again, this is the post that I made. If you want to know the web address, it's forum.digikey.com/t/radio-frequency-terminology/7325. That's right up here. But band pass and band reject apply to filters that either pass or reject frequency ranges. When you get into like control systems stuff, there's a diagram called a Bode plot. When you look at RF signals, the x-axis is the ever-increasing, typically logarithmic scale for the frequency, and the y-axis is the amplitude of that signal in decibel volts. The example below is a bandpass signal I drew up. And I don't think I used a logarithmic scale on the x-axis, but so this would be tip around it can pass anywhere from 270 hertz about to 777.6 kilohertz. This is not a typical frequency range that most devices use. It's just kind of an example to see what's going on. The cutoffs are at 810 and 777 kilohertz. The bandwidth of that particular signal would be 776,190 hertz, or just simply 776 kilohertz. All the other frequencies beyond that range would be severely reduced or attenuated. You can never truly get a vertical 100% cutoff for any type of frequency. The opposite filter is called a band reject. In this case, any other frequency other than the approximately 270 on this and about 780. I didn't quite use the same range, but all other frequencies would be rejected and all other ones would be passed. So these frequencies would be severely reduced and the other ones would be amplified or at least close to the 0 decibel point. You will find these diagrams very common in RF data sheets, but it can be kind of difficult for a layman to understand. It is a lot more messy if we were to describe a sine wave that did this kind of thing. To show you what that looks like, let me just zoom in here. So this is the same bandpass diagram as this one. It would be a ever-increasing frequency sine wave that starts slow and ends up extremely fast with a attenuation near 0 volts, and then as the filter starts working properly, it gets amplified up to a maximum of like 1 volt, because that's what I think that's what the reference point is for 1 or 0 decibels, I believe. So this is kind of what it would look like. This is what it would look like if it was an actual sine wave representation of what this does. So this is a lot easier to understand than trying to do a sine wave thing, because as you can imagine, data sheets would be hard to read if this was the way it was. So broadband, it typically is understood better if it's kind of a loose term when you talk about internet. There is a general term in the RF world. Broadband simply means an antenna that has a wide range of frequencies and potentially several center frequencies that it operates best at. So, yeah, broadband could applies to specific antennas too. It's not just like an internet thing. Gain is could mean a lot of different things, but it's typically an increase in some sort of signal property. With antennas, the gain is not increased power. Antennas are not capable of boosting power, but kind of a directional gain, meaning that, again, an antenna will work better if it's pointed a certain way because it's shaped a certain way. Signals produced from an antenna have directionality due to design. Technically, more gain is not always beneficial with the directional stuff. Less gain is required if you don't want the signal in specific directions. Directional gain is dependent on the application, and that's why some antennas have negative gain or losses. If you're talking about a filter or boosting signals, gain can apply to other units of measurement. You can have an increase in power, current, voltage, but it does require external power to do so. Otherwise, you'd be breaking physics. Return loss is a way to describe the ratio of frequencies that are accepted and rejected by an antenna. VSWR stands for voltage standing wave ratio. Standing waves represent power not accepted by a receiver and reflected back on a transmission line. The best way to describe that is if you have mismatching input and output, like resistance. In the RF world, it's impedance, but you can kind of think of it as the same way. If you have a mismatch, one particular frequency will not see them as the same, and some of that energy will be bounced back across the transmission line. That is not an ideal situation for lines that carry frequency or even like airwaves. But VSWR, to get back to that, it's the ratio between the maximum and minimum voltage on a lossless line. So basically, you're considering the line as an ideal transmitter. Standing waves highly depend on the impedances of the transmission line, receiver, and transmitter, as I was explaining. Impedance is a combination of reactance and resistance. Reactance is also measured in ohms, but is completely dependent of the frequency of the signal. I do have a different post on the tech forum at digikey.com. It's a quick explanation of impedance. I might cover that in the next video. But anyway, so that's kind of like a generic overview of like radio frequency terminology that some might not have experience with. Yeah, so I'll probably get into the concept of impedance next, and then I'll get into how frequency filters work. So thanks for watching, and I'll see you in the next one.